Well, today I'm going to talk mainly about some of the ways in which we measure time. But before we get onto the subject of time itself, there are two elementary principles which I can demonstrate in connection with measuring length, which, elementary though they look, are in fact tremendously important. And the first of them, I would like a volunteer to help me measure the thickness of a piece of paper with a ruler. So, can I have... Now, we have a piece of paper here. Do you think we could measure the thickness of that with a ruler?
No.
Good for you. And, well, obviously, why not?
Because the measurements on the ruler are too big.
That's right. In fact, the paper is thinner even than one of the divisions on the marks on the ruler, isn't it? But, look, if we take the paper and we fold it once, we've got two thicknesses. Twice, four. Again.
8.
Again.
16.
And again, 32. It's beginning to get fairly thick, isn't it? And if I squash it up hard...
4 centimetres.
4 millimetres. So 4 millimetres divided by 32, that'd just be a little over a tenth of a millimetre, wouldn't it? Well, we can check because we have here an instrument which would very precisely measure the thickness. And if I can put this through there like that, and we can squeeze this up like that until the pressure tells me that on that. So
Slowly. That's it.
That's it, okay. And it's reading there just over 10, isn't it? So that's 10 hundredths of a millimetre, in fact, a tenth of a millimetre. So even with our ruler, we got within a few percent of the thickness of this piece of paper just by using a little ingenuity. That's right. Thank you very much. Okay. So this is a very simple illustration of sometimes how thought will enable you to use inferior tools to do a job which perhaps you might at first sight have thought impossible. And there's another one that I'd like to show. And again, I need a volunteer for this, because distinguished scientists might tell you that it is you cannot produce a result of an experiment more accurately than the accuracy of the smallest observation that you can make. And what we want to do here is we have a ruler, and we want to measure the distance between these two marks. Now, assuming that we can only measure to the nearest scale division, if we put the ruler so that the 0 is against one mark, can you tell me what is the nearest? 30. And indeed, no matter how many times we put it down, if we use the ruler in that way, it will still give 30. Now, what I want you to do, and I'll take the numbers down, is not to look, but put them down like that, and then you see that is nearest 7, and that indeed is nearest 37. And indeed subtracting, we'll still get the answer 30. But let us do that 10 times, and I will write down the numbers. You call out the numbers from the left hand and the right hand, having every time just shuffle the ruler without looking at it and take it at random. So if we start now, the first number,
10 and 40.
10,
And 40.
40. So that is 30, yes.
14 and 44.
44, that is also 30.
6 and 37.
6 and
37.
37. So we've got 31, yes.
17 and 48.
48, so we've got 31, yes. Just
4 and 34.
34, so we have 30, yes.
14 and 45.
45, 31. So we want another 4 measurements.
2 and 32.
Sorry?
2 and 32.
32 and 32. 30, yes.
13 and 44. Oh, 43.
13 and 44.
Yeah.
31 and
20 and 50.
20 and 50. 30. One more.
11 and 41.
11 and
41.
41. 30. So the average of that is going to be 30.4. Now, I can tell you that it is in fact 30.3 if we had a more accurate measurement, and by taking 10 measurements and only each time reporting the nearest one, providing we take the measurements truly at random, we can get an average which is almost 10 times as accurate as from the measurement taken in the conventional way. And the lesson there, two lessons. One is the value of ingenuity and insight, and the second is, of course, that it is done at the cost of time. So accuracy costs time. And thank you very much. And and now we want someone to help us as a bomb aimer. So, and what the test of accuracy here is dropping these balls. It would be best if you give them, I think, and dropping these balls into that cylinder, and we will see how many of that size of ball you can drop into that cylinder in, let us say, half a minute. Okay, you start. I think you could afford to have some more and aim more carefully. Try and sight them, don't... Yeah. Quickly, I'll give you a... Hooray, so in the half minute there are 5, is it in? Now, we would do the same thing, asking for more accuracy with that size of cylinder. So 5 went in the half minute. Now, aim as carefully as you can. Well, now let's go back to the bigger one. Now he's had some practice, and we'll feed him with as many balls as we can to see. Now, Well, that's good. You see, already in half the time, you've got rather more balls in. Now you've had some practice with the larger. And obviously, the more, the smaller the target, the more time you've got to take to aim to each one. And so this is yet another example of this very important law in taking measurements, that if you want to get a more accurate result, you've got to take more time and quite often more trouble. The same as we did here. Thank you very much. Well, now, you see, we've begun to get a relationship between measurement, even of simple things like length, and the time that we take to make the measurements. And so our ideas of time are as difficult to explain as the ones I was talking about last time, of just as you can't put an idea of number very easily into words and an idea of length. These are, as it were, fundamentals to our whole system of observation and reasoning. So it is with time. We all know what we mean by time, but to put it into words and try to explain why it goes always one way and time doesn't run backwards is, of course, one of the literally eternal mysteries. And for measurement of time, there are 2 or 3 basic methods, one of which is a process, exploiting a process which is known to take or is assumed that it will take the same time every time one does it, rather like the hourglass, like the the egg timer, and the device, the ancient water clock, which should come up on the first slide, which was an invention of the ancient world. That's a misfire which is already corrected. And here is a drawing that I found in an Arab book of scientific designs, where the designer was making rather elaborate water clocks in order to please his prince. And the basis of this device is rather like the hourglass, a conical vessel which is filled with water, and there's a small hole at the bottom through which the water gradually flows out. As it does so, the level in the vessel, of course, falls, and the dimensions of the vessel are chosen and the shape is chosen so that roughly it falls by equal distances in equal times. And to make the device attractive and easy to read, what the designer has done is to measure the water level with a float which moves up and down this rod here. So when the water's at the top, the float is at the top here, and attached to the rope, or the float, there is a string or cable going round a reel here, and then is kept taut by this weight here. And however, the weight here is not as great as that of the float, so the float always will go down like that, causing this reel to move round as the float goes down. And the device is made to look ornamental by putting a human figure on the top with this pointer, which points to a scale arranged round here. Well, that was the kind of device, in fact, almost the only kind of device that we know of, these devices where something gradually runs out, until men began to exploit the rhythmic or periodic phenomena that we use today. And we ourselves incorporate, all of us, one which does approximately the job. And that is, of course, our heart. And if we feel our pulse, we can feel it beating, I hope, fairly regularly. And I want to tell you of 2 of the very important discoveries in physics, which were made with nothing more than the human pulse. And of course, it took a very great scientist indeed, Galileo, to do it. Here is a portrait of Galileo, and one of the things he did was to establish that when a body fell under gravity, it covered a distance which was proportional to the square of the time of fall. Now, the times are much too short for him to be able to do this directly, but he, as it were, diluted the effect by, instead of letting the body fall vertically, by letting it run down an inclined plane under gravity. And you can all try and do this with me. What I'm going to try and do is, when Mr. Coates lets the ball go, to time it in my pulse beats to there, which is 1/4 the way, and to the further white stop, which is halfway. So I will try and get my pulse as steady as I can, and I'll give Mr. Coates a 3, 2, 1, off, 1, 2, 3, 4, 5, 6 and a bit. We'll do it again, and you may all try this for yourselves. See if you can feel your pulses. You won't be synchronized with mine, but nevertheless, you may be able to see the effect. 3, 2, 1, off, 1, 2, 3, 4, 5, 6, a bit. Well, as my pulse is going, it's going slightly faster today, this afternoon, than it was this morning, perhaps because I'm excited a bit. And it was about 3.5 down to here, but in twice that time, it had covered 4 times the distance. And to make this, show how accurate this is, the apparatus here, which belongs to the Royal Institution, Mr. Coates will now set up to do it with a slope which is appropriate, and distances down here, you'll see, pull those off like that. We can pull that one off, Bill. And that is 1 squared, 2 squared, 3 squared, and 4 squared. And you will find that it takes equal times to go through these increasingly greater distances. And the thing is so arranged that Mr. Coates can time it with the metronome, and we can see the then it did it. Okay, do it again. Well, we've now given a more exact demonstration of what such a great scientist as Galileo was able to deduce simply by his pulse beat. And the other very important fact of mechanics, which he found by exactly the same technique, I think it may have been watching the great incense burner in the cathedral in Padua. And by watching this swing, he established, as we can see here, and I think we'll have an imitation incense burner, and here it is. And the first thing he established was that of a pendulum of a given length, occupied about the same time for its swing, whether it was swinging through a small arc or a large one. And so, again, 3, 2, 1, off, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And now we'll let it swing through a much larger arc, if we can, or a smaller one, it doesn't really matter. And so again.
3, 2, 1, go.
1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And so now he had something which, irrespective to a large extent of its amplitude of swing, kept the same period. A very valuable invention from the point of view of now of counting time. It didn't matter how far it swung, the time to repeat was the same. He also showed that that the time of swing was proportional to the square root of the length, exactly by the same technique as we were using there. And he also showed that whatever mass you had here, it also made very little difference. And here we can have a volunteer who is obviously of a different mass from this which I can hold up. And okay, and we'll see how they keep time.
3, 2, 1, go.
Fine. Well, now Galileo had the basis of a nearly constant timekeeper, and it was very quickly applied to the development of the pendulum clock. And you really want two things with a pendulum, you see. One wants to have a system which will oscillate, but because of air resistance and friction, it will gradually die away. So you need something, a source of power, which will give it a nudge just at the right point to keep its oscillation going, and also to count the number of swings or the nudges. They're the same thing. And this was achieved by the invention of the escapement, where the driving power, due to this weight pulling down here, is trying to make this wheel turn, and it's not doing very well just at the moment. Let's see if we can. It's not doing well, is it? But it alternately captures the wheel and allows it to escape. And this is why it's called an escapement. And it edges the wheel round, and it is that movement which one can now indicate by a pointer. It also makes the tick-tock that you can hear. And it's the invention of the escapement and allowing it to drive the pendulum by providing extra impulses to overcome the effect of air resistance and so forth on the one side, and the fact that it inches round by one tooth every time, that gives the basis of the pendulum clock. And of course, once that was invented, a fairly accurate measurement of time was possible. But there was one, and perhaps the most important application of measurement of time, which the pendulum clock could not satisfy. You couldn't take it to sea, or if you did, at least the ship rocked about so much that it disturbed the pendulum. And the premium on timekeeping at sea was just this, that it would help you to know where you are. You see, if you're in the middle of the Atlantic Ocean here, out of sight of any land, it's not too difficult to establish your latitude, because one knows exactly how the sun is moving relatively to the Earth, and at any time in the year you'll know the height above the horizon at noon for any particular latitude. And so immediately you observe the sun at noon, you can get some idea of how far round the Earth's curve you are. And that's an easy measurement to make because it just means measuring an angle. But longitude is far more difficult. And the process by which sailors would hope to do it was just this, that, for example, supposing the sun is in this direction, like that, and it's overhead at noon at Greenwich here, well, gradually as the Earth turns, like that, it's now noon in Canada and the eastern United States, but that's 5 hours later than it was here, because it's taken the Earth 5 hours to turn through this angle. And so there's a direct relation between the lag of the sun appearing at noon here and at Greenwich, which will give you a measure of how far east or west of Greenwich you are. But that's all very well, but how do you know when it was noon at Greenwich? Of course, now it's easy with radio signals, but there was no radio, of course, in the 17th and 18th centuries. At the time when the sailors from the Western European nations, and our own in particular, were navigating or trying to navigate all over the world, and safe means of finding the right places on far distant coasts were extremely important. And so there was a great prize to be had for anyone who could make a clock that was so accurate that you could take it to any part of the world, and having set it here, it would keep exact time with a clock in Greenwich, so that although your local time, judged by the sun, was at some particular value, the fact that it was so different from what it was at Greenwich would enable you to calculate how far round the Earth, one way or the other, you were. When I say a great prize was literally to be had, that was true in that it was so important that the British Admiralty offered a great financial prize to anyone who could make a clock that was accurate enough to do that. And it had to be something different from a pendulum clock. And in the preceding century, Robert Hooke and Christian Huygens in Holland had invented a quite different kind of timekeeping mechanism, which also used an escapement, but used, instead of gravity as the restoring force, the restoring force of a spiral spring, and instead of the bob of the pendulum, the inertia of what is known as a balance wheel, concentric with the spiral spring. And this model shows in slow motion how that timekeeping mechanism, which became the basis of the pocket watch and was developed by John Harrison into the marine chronometer. That shows how it works. But to take that mechanism and make it into something which is good enough for the purpose, and to work in different conditions of temperature and in different positions as the ship rolls, for day after day, was one of the greatest mechanical challenge of the 18th century, and really for long afterwards. And a tremendous amount of ingenuity and painstaking investigation and design went into the design of the spring chronometer. Now, in connection with the chronometer and its development, there are many interesting stories, but one of them I would like to tell you about its early trials. And for this I want to recall a point in British history which seems to be so different and so little connected, the Battle of Quebec. Can anyone tell me the date of the Battle of Quebec?
1759.
Good show, right. There were also two other famous victories that year. There was the Battle of St. Vincent and the Battle of Minden. And in fact, it was known as the Year of Victories. Well, what happened at the Battle of Quebec, or as a result of the Battle of Quebec?
Canada was won.
That's right. And who was the general at Quebec? General Wolfe, good. Well now, how was it that the British Army was able to surprise the French at Quebec when the French generals had been advised that the British Army could not be there because the St. Lawrence River was so dangerous and so full of shoals that a warship of the size of the British warships couldn't possibly be navigated up there. The answer, and this I think is the first case in history where really precise measurement has affected the outcome, not only of a military campaign, but a whole great country like Canada. The feat was achieved of getting the British warships there by virtue of this map, this survey, the chart of the St. Lawrence River. All these dots which you don't show up very well are in fact the soundings that had been taken, and the whole thing is charted so the British fleet could come up here. They actually laid false buoys to make the French they were going to land somewhere else once the French found they'd got up as far as here. But they laid a false trail, but they nevertheless came up here, and they landed, as I would hope you know, some of you at least, below the heights of Abraham, and surprised the French. Well, you may have seen the name on that chart. It was Cook's chart. And the man who made the chart was one of the most famous of all navigators, Captain James Cook. And by 1769, James Cook, with a copy of Harrison's chronometer, which was on the slide very briefly here, set off on the Royal Society expedition to New Zealand, partly to find where New Zealand really was, and also to chart it and make astronomical observations there. And Cook's chart of New Zealand, and this just shows A, what a splendid choice he was, and B, what an admirable navigator he was. And with the aid of the chronometer, and he was 3 years away from Britain on this voyage, which took him all over the Pacific. He not only found New Zealand, he charted it, and this is the chart. The green is Cook, or shall I say, for the benefit of viewers in black and white, I'll run around it here. The one here, which if you've got colour, I hope you can see in red, runs like that. And you can see he's got the shape almost perfectly. And the biggest errors between his position, according to his measurements, and where we believe or know New Zealand is today, is at most 30 to 50 miles. This after at least 12,000 miles of sailing. And indeed, after more than 3 years away, when they came back to this country, they found that the chronometer was only, over all that time, only 7 minutes and 45 seconds out. It was a tremendous achievement, both for the chronometer and, of course, for Cook. And improvements to chronometers and pendulum clocks went on right up to, it's still going on to some extent, but they've now been, for the most accurate measurements, superseded by other techniques. And the first of them that I want to talk about is the quartz clock. And what I've said is this, that a system with a spring or with a pendulum, you want a system which will oscillate, you want something which will give it a nudge at the right time. So the system, as it were, has to tell the source of power when it wants the nudge. The source of power then has to apply it, and then count up the number of times it makes the application. And quartz is really just a spring. And it's different from some other materials that not only does it exert a force if you stretch it or try and push it and compress it more than it wishes to be, but at the same time, an electrical charge difference appears at the top and the bottom. In other words, it manifests electricity as a result of pressure. And this is known as piezoelectricity. And although they're not quartz, they're something which would develop still higher voltages. You may have seen some such devices in gas lighters, where if one puts it here, one can generate so much charge that one actually gets an electric spark, which will ignite the gas. Again, one could talk about that because it's a big danger in coal mines, because if steel strikes a flint in coal mines, you can get a spark which can start off a dangerous explosion. But also, it can be used as the basis of a clock, because if we look on the overhead projector, I can show you roughly what will happen. In the meantime, I can show you the piezoelectric effect. Yes, because in here, under here, I have a piece of material which does show this effect. If one puts in a piece of ordinary material like aluminium, like that, and puts it inside the clamp there, when I press on it, there's no effect, you see. But if I take that out and put in this other material, like that, and now press, if I press, it goes one way, and when I let off, it goes the other way. Supposing this is its normal position, if for some reason or other it's expanded, the expansion creates this difference in voltage. It springs back, but just like this spring springs back too far, see, it would normally be there, but when I let it go, it comes back to here. Well, while the quartz is in that position, it generates a charge of opposite side on its faces. And then, of course, it springs back again. And so one gets alternately a positive voltage, negative voltage like that. And if you can arrange an electrical circuit to give it the nudge at the right time, then you can keep this oscillation going. And what is more, you can count the nudges, and you've then got the basis, as it turns out, of a very accurate clock, because quartz is such a good material. It's a single crystal, and it's very stable, in fact, more stable than the best pendulum or spring clocks. And the only trouble is that it oscillates so quickly that until recently it was difficult to count the oscillations. In watches, how many of you have got a quartz watch? Yes. Well, now, those little bits of crystal will be doing this at least 32,000 times a second, and quite a number of them will be doing them at over 4 million times a second. These are, in fact, to a given power, either 2 to the 15th power or 2 to the 22nd power, and by a series of dividing circuits, like the counters we were talking about the other day, and dividing down by a factor 2 every time. If you do it 22 times in one case or 15 times the other, you get down to a regular second. And that is the basis of the quartz clock, which has made everything so very precise. And even more precise than the quartz clock are atomic clocks, where now it is possible to relate time directly to vibration phenomena or oscillatory phenomena connected with atoms. And by picking the right atom, which can be put into the right kind of apparatus, one can develop a very precise timekeeper. To do the actual counting like this, you can convert the original sine wave into something like a square wave to give the pulses your electronic circuits just by a simple process of amplifying and then limiting the amplifier output like that. And so what you get out is like that. And if we can have the next slide, you can see the progressive improvement since Harrison invented the chronometer, when roughly the timekeeping was about a second a day, to the quartz crystal clocks here, which are good to a second, the best ones in some years. And now with atomic standards, the best of them so good that they're accurate to about 1 second in 30,000 years. And they're so good, in fact, that you can see that our dear old Earth, which we've taken as our standard timekeeper for all these centuries, really isn't as accurate even as one of our quartz crystals. And not only can one see that the Earth is gradually slowing down its rotation, this is partly due to the tides, the drag exerted, the tides caused by the moon, but also over the recent years when we've had these very accurate measurements available, one can see that at some times during the year, the day is almost 1,000th of a second longer than at other times, if you judge the day by the Earth's rotation. And we are fairly sure of at least what the cause is, which we could demonstrate with another volunteer. If one likes to come out and pretend he or she is the Earth. Now, if you get on, because it'd be a good thing, I think, if you would hold these. Are you all right? Yeah. Or shall we try it without these first and see whether all is well? Because if you'll hold your arms out like that, I will spin you round. Any ballet dancers will know. Now bring your arms in. Right. Well, now you're all right at that. Let us put some weights on. And can you hold those out at arm's length? Right. Now, okay, bring them in. And out again. You see, you slow up. And in again. And that is what the Earth is, we think, doing. Let me help you off. Right. Okay. Thank you very much. This is the phenomenon known as the conservation of angular momentum. And because the polar ice caps are bigger, or certainly the northern hemisphere, of course, in winter, and also because there are big movements of air masses associated with the seasons, the Earth alternately spins up and slows down again, rather, of course, on a minute scale compared with the model. So much so, I'll go at least with the volunteer, so much so that no longer do we define the second as 1/60th of a minute, which is a 60th of an hour, which is a 24th of the Earth's rotation, but we actually count it in this enormous number of oscillations of radiation coming out of a transition in the cesium atom. And you can see it's an enormous number. The first is 9,192,631,770. And so we now have at least one of our standards related to fundamentals, atomic phenomena, so that even if all our ordinary standards were destroyed, provided we could find the cesium atoms again, and we could count at this speed, we could completely re-establish our system of time. Well, these are the things which we can measure with clocks and similar devices. But when we have to go back in time, where there weren't any clocks, then we have to look at other methods. And one which has been quite useful is the one which is exemplified by this cross-section through a tree of European larch from Argyllshire, which has been lent to us by the Royal Botanic Gardens at Kew. It happens to have been a particularly good tree and certainly grown surprisingly rapidly for Argyllshire, so much so that because a tree grows much more in summer than in winter, you get alternate layers of fast growth and slow growth, and you can see them, and from the relative widths of the layers you can tell what kind of summer it was. You can see climatic changes like this. Well, this tree is only 115 years old, and it shows up the rings very clearly. The oldest trees in the world, the bristlecone pines in California, will enable us by similar techniques to go back for perhaps 2,000 or so years, perhaps a little more. And we can go a little further with exactly the same phenomenon, but now looking at the deposits of clay in sediment in lakes, where again the sediment rate changes according to the amount of water coming into the lake, which depends on whether it's summer or winter and so forth. And you can count back here at least for 26,000 years by this technique. But after that, these techniques begin to fail. And we almost go back to the original kind of clocks, those which run out. But we want clocks which will run out over a very long time, of course, rather than the few hours of a water clock. Well, fortunately, when radioactivity was discovered, it was realized that this was, it were, because of nuclei of a particular kind running out, because they were actually decaying. And Dr. Evans here has very kindly come along to give us a demonstration of radioactivity. The atoms with which we are interested for timekeeping on the long scale are ones which of course take a very long time to die away. But in order to show that the phenomenon can occur and one can see on a very much accelerated time scale the kind of thing that can occur, here we have a specimen of radioactivity from the protoactinium nucleus, where these nuclei, which are made as a result of a uranium decay, they themselves decay with a half-life of a few minutes or so, and Dr. Evans will separate them out, put them into the Geiger-Müller counter, and we'll hear them being counted. But while he's doing that, we'll look at the next slide, which tells the history of men's ideas of the age of the Earth, because in the old days, first of all, there was Archbishop Usher, who said the world was made in 4004 BC. But then, as scientists began to work it out, there became one of the great controversies between the physicists and the geologists. The geologists wanted hundreds of millions of years. They couldn't believe that all the things they saw in the way of sediments and in evolution could possibly have occurred in shorter than several hundred million years, whereas Lord Kelvin had believed that it would take a good deal shorter. And in the end, the evidence that clinched the matter, fortunately, came from the physicists who were able, therefore, to re-establish their credit, and it was because of the evidence from radioactivity. There are the protoactinium nuclei decaying, and you can hear all this scratchy sound is the impulses given to the counter by each one as it decays. I think we can switch off the sound now, but we can leave the meter running, because the meter indicates the rate of decomposition, and I think within 2 minutes we shall see that there is decay occurring, and the rate of decomposition will be less. But if I may take a quick look here to catch up with this, you see, if you take the two uranium nuclei and assume that they were equal in numbers at the point of creation, which they very possibly were, then because the half-life of uranium is 235, is much shorter than that of 238, this is 730 million years, at any point afterwards, the ratio of the one to the other is changing, and from their present ratio, we can extrapolate back to when there would have been the same numbers, and we assume that that was somewhere about the date of the creation of the universe as we know it. By the time the Earth's crust solidified, it was somewhere about here. Well, a lot of this, of course, is a large-scale extrapolation, but I hope I've given you some idea of how we do go back in time. And to finish with, I would like to show you a measurement of a very short time involving the time taken by a pistol bullet to go between these two this. Now, my students here, when they see this series, will think that I've chickened out, that I'm too worried to fire a pistol in front of an audience on television. It isn't that at all. One of the most famous of physicists I've mentioned, Lord Kelvin, used to demonstrate an experiment in which, as he got older, his sight became rather less good. And on one occasion he did miss the target, and it went clean through. It was an elephant gun he used. It went clean through and made a hole in the blackboard of the lecturer next door. Lord Kelvin rushed in to see what had happened. He found a white-faced lecturer, and the class promptly shouting, "Missed him, shoot him again, Bill." But we will do it by getting Mr. Coates to fire the air rifle. I would like to have done this with a pistol, but public safety regulations forbid it, and so we have in fact done an experiment when no one was here with the pistol. We can give you the answer for that too. But to demonstrate the method with the slower velocity of an air rifle pellet, I'll ask Mr. Coates to fire at the target. One's got to be very careful to try and fire on a line parallel to the axis, of course, and like that. We let the motors rev up. And then slow down. And then we can trace the bullet hole like that. And you can see that there is a big lag between because this disc had moved all this way round while the bullet was going across. Now what we have to do is to measure this angle. And which one would you like? It's a bit complicated because this protractor was made for the pistol, which has a higher speed and therefore is a smaller angle. And it only runs up to about 40 degrees. So we'll take the mark at 30, and then we move it round to the 30. 30 plus
14.
14.
I've got 54.
So it's 44.
54.
Sorry,
44.
30 plus 14, 44. So, and the speed we believe was, we measured it beforehand as 2,750, was it? Yes.
I've got 22,500.
22,500 centimeters a second. So dividing by roughly 30 to get to feet per second, it's around just between 750 and 800 feet per second, I think, if I've done the sums right. Now, although this is a very elementary method, it is a very important one because this was a way in which the speeds of molecules was found. One could fire molecules not through with a slit in the disc here and find where they fell there. They gave molecular speeds in this way and found indeed that the speeds of molecules were in the order of 50,000 centimeters a second. And also, if you can imagine this disk bent back on itself here, by sending light through the disk and out to a distant mirror and bringing it back, this is in fact what Fizeau did to determine the velocity of light. And the other thing that I'd like you to notice, that you can learn from this experiment, is that the bullet going through, let's take that mark and this one, we know, in our frame of reference, that that bullet came through parallel to this axis. But an observer going round with the disks would say, I know where that bullet came from. It came, you see, from over there. Quite a different angle altogether. And this is exactly what light happens to light as it travels down our telescopes. The direction of the starlight appears differently at different times here, depending whether the Earth is going on this part of its rotation or that. It's a very important effect known as the aberration of light, about which we may say something in a later lecture. Thank you very much.